Okay, let's go ahead and get started again if that sounds good to John and everyone else. We have Volkan Ustun and Paul Rosenbloom with us, presenting on the Sigma cognitive architecture and system.
Thank you. Hello, I'm Volkan Ustun. I'm a research scientist at Institute for Creative Technologies at University of Southern California, working for Dr. Paul Rosenbloom for a while now. And I'm going to be talking about the Sigma research. Sigma started and still led by Paul Rosenbloom. I have been part of this thing for the last 8 years, and there are many other contributors. And for today's talk, I would like to thank Lixing, Jincheng, Rajay, and Sarah. So I'm gonna first I'm gonna introduce Sigma and discuss what Sigma is about. Then I will try to go into some of the more exploratory research areas that we have, one on conversational question answering and other one is towards a neurosymbolic reasoning and structured learning for Sigma. I'll briefly touch the other research that is happening in our lab before I conclude. So at the Cognitive Architecture Group at ICT, we are striving to create human-like autonomous social cognitive systems. And this requires the integration of different abilities like perceiving, reasoning, acting, learning. And also, you need to have the interaction capability, communicating naturally, both verbally and non-verbally with others. You should have the capability of theory of mind. You need to have affection, be motivated, and to show some exhibit personality. And there have been lots of research and lots of state-of-the-art results happening, all of these individually. But still, developing a single system that integrates them is very challenging. So I think this is not a very relevant slide for this symposium, but the question is why we are going after something human-like. First, this is a fundamental science question, but trying to understand what is common between natural and artificial intelligence. And also, it is required by the applications that we are interested in. And in these applications, we would like to substitute human participants in simulations, creating non-player characters, which can interact more naturally with other human users and teammates, and also improve the robustness and resilience of these characters. So thinking about all of these, cognitive architecture creates a compelling candidate to address all the issues and gives us a tool to create these human-like social cognitive characters. And one question over here is, okay, why we need cognitive architecture, or what is good about cognitive architectures while creating these characters? In general, I would like to address it this way. I mean, first over here, using a cognitive architecture allows us to leverage common fixed processes that are already existent in the cognitive architecture. And we can constrain for cognitive plausibility to provide guidance for human-like models. And if the cognitive architecture is actually inspired from human-like systems, creating human-like systems, it helps us to validate the cognitive models that we have created. This is especially true when you have a conceptual valid basis for the cognitive architecture, and the common model of cognition gives us a huge leverage to argue the cognitive conceptual validation of our architectures that we are working on. And finally, cognitive architectures are designed to integrate various capabilities, and this allows us to integrate all the capabilities that we are discussing, and we believe it is important for creating human-like social cognitive systems. So Sigma is basically tries to combine what has been learned in 40 plus years of work in cognitive architecture, graphical models, and neural networks. It defines a cognitive architecture on top of a graphical architecture. Cognitive architecture defines the cognitive language to define cognitive models, and all of these compiled down to a graphical architecture where we use extended graphical models. So graphical models allows us efficient computation over multivariate functions. And here we are using a factor graph representation as the basis for Sigma. and also use a sum product algorithm as a message passing algorithm to drive inference on those graphs. And graphical models gives us a uniform processing of symbols, probabilities, and signals. And for sigma, we have extended this graphical model representation by hybridizing it. In a way, we extend the factor graph representation to allow asymmetric message passing. And this was one of the foundations of sigma, where rule-based modeling or rule-based inference is driven by asymmetric message passing on factor graphs. More recently, we have added appropriate nonlinearities like sigmoid or rectified linear units, and also adding separate but paths to allow for backpropagation by leveraging function tying. We are able to show that using this factor graph representation, we can efficiently run neural networks and do backpropagation in sigma. So sigma cognitive model uses predicates to define relations among typed elements. It leverages conditionals, yield patterns over predicates, optional with functions. And here, in addition to standard condition action pairs, we also have condacs which show bidirectional message passing or bidirectional interaction between two predicates. And we also have Soar-like nested tree-level control, where you have a reactive layer, which is the inner cycle for a deliberative layer, which is the inner cycle for a reflective layer. And everything in sigma, the learning in sigma is based on gradient descent, local gradient descent. So gradient descent is a local incremental search for optimal weights. And in the sigma's graphical architecture, the gradient defined by the messages coming into factor nodes. And by leveraging gradient descent learning, we show that we are capable of a variety of different forms of learning, including episodic learning, concept learning, reinforcement learning, simultaneous localization, mapping, and neural networks. But this is, at this point, only parameter learning, and we are looking for ways how to extend this thing to structured learning. So this is some simultaneous localization and mapping model. So here we are trying to learn a function or a map in the object location map or object location X predicate. And it is interacting with the current location, which objects are seen, and by bidirectional message passing, while we are learning a map, we can simultaneously affect the agent's current understanding of its current location. And we can also do reinforcement learning in similar way by backing up values and rewards. So sigma, the general Desiderata for sigma cognitive architecture is, it's a new breed of cognitive architecture that is trying to be grant unified, combining key cognitive and key non-cognitive capabilities like perceptual, motor, affective, and attentive. It is spanning both natural and artificial cognition, and it's trying to be functionally elegant. And it's also trying to be sufficiently efficient. So sigma is based on three pillars. One is the factor graph representation. The other one is the local gradient descent learning mechanism. And finally, a general sum product message passing algorithm shows the three pillars of sigma. And every other capability in sigma is trying to be achieved by micro variations on these key capabilities, unless we hit a major blockage on our road. And so far, we were able to show many capabilities can be achieved, can be generated by micro variations on these three key pillars of sigma. And sigma, leveraging all of these, try to create virtual humans and intelligent agents robots that can think, behave, and learn. So at this point, I would like to spend a minute on the Soar sigma split. If many of you know, Paul Rosenbloom was one of the original co-founders of the Soar architecture. And Soar started with the hypothesis that there need to be only one form of long-term memory and one form of learning. And Paul and John concluded that this one form of learning in a way failed. So it is, in a way, the combination of rules and chunking, while it's quite broad, it wasn't still broad enough. It wasn't broad enough. So Soar developed a multimodal approach, and it is creating added different structures and processes onto the architecture. Paul wanted to go after a more generalized memory structure where everything is variations on the same basic structures that I was referring to previously, like the factor graph representations, local gradient descent learning, and a message passing algorithm like sum product algorithm. So in Sigma, we have shown different capabilities so far: memory, problem solving, learning, imagery, perception, natural language effect. And we also have few demonstrations of capability integrations. One of them being a 2-agent retail scenario, while there's an intruder trying to steal items where a guard trying to catch him, or an integration in a Unity-like environment where this agent is just using architectural appraisal mechanisms. No knowledge is provided, just leveraging the appraisals. It is trying to locate an item in an environment. And for this, it is using attention, desirability, and surprise while learning a map of the environment. And also it is leveraging architectural appraisal like curiosity, where it is using, again, familiarity with the environment and try to explore different areas of the structure to locate the item in this layout. So here, the key point is there's no knowledge added to the SIS model. It is just leveraging the architectural appraisals that's gathered in the cognitive model. So this is the general introduction to Sigma architecture, and we are still working on models on showing different integrations and try to leverage Sigma, utilize Sigma models in a variety of simulation models. But I would like to spend this opportunity to spend some time on how we are thinking about different opportunities and how we are trying to explore different areas where we can augment our understanding and believe cognitive models can benefit from. So one is conversational question answering. This is basically responding appropriately to questions about a narrative in a dialogue. And the motivation over here is synthetic characters in simulation environments. They need to have conversation capabilities. And most of the time in these simulations, the context of the conversation is defined by role of the synthetic entity in the training simulation. And if exists, there is the conversation history that synthetic entity had with other characters or the trainees in the simulation. So the idea over here is, rather than training these synthetic characters on the dialogue, we can train them on extracting information from a variety of channels to assist generating utterances. So these channels could be the scenario descriptions, tactical doctrines, which could be of text-based, the conversation history, either it could be text-based or directly gathered through speech recognition, and also other modalities like simulation state or situation awareness with theory of mind emotional states. First, we are focusing on the question answering and conversational question answering part. For conversation answering, we basically try to extend the neural capability of Sigma and successfully implemented RNNs and gated recurrent units. And the point over here is this is not implemented as a different mechanism. We basically achieved this thing as our capability by manipulating how we are processing knowledge, and this is that manipulation yielded in implementation of recurrent neural networks within the architecture. And we have used these structures for basic question answering tasks where we are trying to answer questions that are coming from a text or a paragraph or a narrative. Now we are focused, as I said a couple slides ago, basically we are interested in multimodalities and how combine these things together. In a way, we would like to leverage the structure across these multiple information channels. So we are trying to exploit the potential relations that can be defined in these multiple modalities and use this thing to learn and successfully answer questions, create utterances based on these different modalities. So most of the mainstream models, they do not leverage the existing connections between documents. They just concatenate all input channels. And yet they are successful since most of the current data set does not require reasoning across documents. This is changing. This multi-op reasoning, leveraging multiple modalities is becoming more popular in the domain, but still most of the mainstream models are not capable of this. And what we are trying to do is, okay, can we exploit the additional structure in the data by applying appropriate relational inductive biases to the models? And for this, we are trying to investigate and utilize graph neural networks to induce such relational biases into our models. Graph neural networks basically provides us a mechanism to define neighborhood structures between different nodes. And it still uses distributed representations or embeddings at the node level. And it defines a message passing or a neighborhood aggregation mechanism where you can send messages across neighboring nodes. And by aggregating them, you can update the representations at each node level. And you can use graph neural networks for different tasks like node labeling, or edge discovery, and all these things. In a way, this is kind of a leveraging convolution in a relational structure that is not pixel-based image representations, but a more general relational structure. So what we want to do over here is we would like to leverage graph neural networks for a conversational question answering task where we are creating relations, leveraging relations that exist across multiple sentences, multiple paragraphs, different modalities, and see whether we can build up something incrementally in a cognitive way that is capable of capturing what the information that's being conveyed by creating structures over there and can learn to do the question answering task relatively fast, efficiently, without relying on a lot of data. So for here, right now, we are exploring if we can build up these graphs using dependency parsers by defining the words and the relations between words, syntactic relations words, and also if we can use semantic relations across sentences or within a single sentence and create these graph neural network-like structures. And if we train these things on existing data, can we learn effective weight matrices that are defined between nodes where messages passed go through these neural models, and at each node you can have different structures like recurrent structures or other attention-like layers. So by training these things, we can train these weight matrices that learns how to behave in a certain way for different types of questions or different type of mechanisms. And the idea over here is, can we effectively use these structures to learn something about question answering and also build up these structures in an incremental way, hopefully using them, leveraging them as memory constructs that are capable of representing things in a relational and structurally consistent way. The second thing that we are exploring right now is, okay, we want to explore neurosymbolic reasoning in Sigma and structured learning in Sigma, but we have a number of problems before even coming at that stage to explore those ideas. In current Sigma architecture, there's limited support for continuous inference. Sigma only allows approximations with piecewise linear functions, so it is not possible to define parametric continuous distributions in Sigma. It is using Lisp, but unfortunately, Lisp language cannot take advantage of more computational libraries and development in hardware like SIMD and other parallel processing that happens at the CPU level for efficiency. And we need a more flexible implementation of the graphical system for structured learning. And we also want to explore further neurosymbolic reasoning. So here, this effort, we started exploring how to do those things. And as a first step, we kind of started re-implementing the Sigma architecture in Python. But over here, what we are doing is we are being loyal to Sigma's factor graph representation. But everything defined in the factor graph level is compiled down to PyTorch computational graphs and tensor processing libraries. So in a way, we are trying to take advantage of already optimized code base that are capable of doing this tensor processing and a bunch of available libraries to create a more efficient implementation that lies under the graphical layer of Sigma. And while we are doing that, we want to augment Sigma that would make it more ready for types of structural learning that we want to do along with neuro-symbolic reasoning. So we are working on exploring ways to how we can extend the representation of messages. Currently, Sigma uses piecewise linear functions to define any messages, and most of the time we go down to finite discrete distributions represent as tabular messages in Sigma. We are trying, right now, we have defined ways to extend these things to capture parametric distributions, as well as particle-less or particle representations that are still embedded on the same factor graph representation, but different types of messages with different processing. And here for computation, we are leveraging the existing sum product algorithm, but additionally, we are exploring how we can have variational message passing or expectation propagation, both message passing type of algorithms to do approximate inference for continuous functions and for particle models using stochastic exploration or stochastic sampling coming from continuous distributions. So such a framework gives us a chance to a seamless integration with neural models. So here we can leverage what PyTorch already has, creating an end-to-end differentiable message propagation path. And also we can directly integrate all of those neural models with existing current Sigma models and defining all of these within the Sigma cognitive language. Furthermore, we can leverage this thing towards a neurosymbolic integration where we can define, in PySigma, we all can define lifted variabilized parameters, predicates, and also use variable bindings conditionals supporting first order logic semantics. And here we can have a seamless integration with neural networks so that we can potentially exploit bottom-up knowledge summarization and generalization as a kind of form of structured learning over here. So this is something ongoing. We have the initial parts of this thing. It's not completed yet. Hopefully we'll have more results, more interesting implementations out of this. Right now it is just an exploratory thing that we are working on. So other things that we are working on is, again, the simulation models for creating characters in training simulations. And over here, we are trying to look ways how we can integrate Sigma within a multi-agent reinforcement learning pipeline. We have a theory of mind project where we are implementing task models for a search and rescue scenario in Minecraft. There's ongoing search on motivation and personality, as well as porting core Sigma data structures into C. So as a conclusion, Sigma embodies a new approach to cognitive architecture. So it's based on extending a broadly uniform, mathematically sound, and potentially efficient graphical architecture for next generation virtual humans and intelligence agents robots. And it is part of the effort to develop a common model of cognition. As I said in the beginning, it's very important. The common model of cognition is a very interesting and important development from our perspective. And it would definitely inform the conceptual validation of structures, cognitive architectures, as well as to have us a better understanding on the community consensus of structures, processes, and also guidance in research and applications. So I hope I'm on time, but that is it for me.
All right, we're now opening for questions. So we have two questions. First from Stephen. He asks, why do you need learning of new graphical structures in Sigma? Where do you find parameter learning to be insufficient?
Structure learning over there, what I mean by structure learning is learning new conditionals or new relations between different predicate structures that we have in the system. So with parameter learning, we are mostly learning the functions that we have defined in factors or factor nodes in our factor graph representation, but that's not enough for us to extend our learn explicit relations that is not predefined or pre-modeled in the cognitive model.
Okay, I think Stephen can message in the chat if that doesn't answer his question. So Keith asks, has any graph theoretic or topological notions, for example, Brewer's fixed point theorem, been used in the optimization of graphical structures?
We have not necessarily looked into any of those things to optimize the graphical topology. We are compiling these graphs from a knowledge-driven perspective to allow us to certain processing, creating the relations, defining the predicates, and capturing the relations that are defined in the conditionals. But we have not necessarily looked at how to optimize those graphs.
Okay, thank you. Another question from Stephen. He says, I admit that I haven't inspected Sigma's code. Do you have an implementation of all of the common models memory systems all running together, all implemented in terms of factor graphs using efficient Python libraries to do the factor graph computation at the bottom layer?
So we have an implementation of memory structures in the current list-based Sigma code. So we have the semantic memory and the procedural memory implemented that way. We have an example of episodic memory, which interesting characteristics, but the implementation of the episodic memory, I have to admit, it's not very efficient as of now. The Python version of Sigma is still in process. It's not completed yet. It's going to have this exact same functionality that Sigma has, probably augmenting those capabilities, but it is not there yet.
Okay, thank you. It doesn't look like we have any more questions. So we have, Peter Yu asks, when would that be ready?
I don't know, and hopefully we will start testing it within the next couple of weeks. But when it is ready, I don't have a good answer for that right now.
Thank you very much. We have a couple minutes